Hello, my name is Carlos. I am a student in the University of Amsterdam, and I would like to start thanking Enrico and Guilherme for organizing this nice workshop. So in this talk, I'm going to tell you about weight shifting operators in the context of the cosmological bootstrap. This cosmological bootstrap is a project that started roughly 2 years ago with this paper by Nimar Kani-Hamed, Daniel Baumann, Hayden Lee, and Guillermo Pimentel. And then two more papers have followed in which Austin Joyce and myself joined the collaboration. In this talk, I'll talk about the weight shifting operators, which is an aspect of this project, which was mainly developed in this paper. Then later, Austin and Hayden will give a couple more talks in which they will present the nice results of our last paper. Okay, so this is a brief outline. I'm going to start by introducing the general philosophy of the project and motivating the need for weight shifting operators. Then I will introduce the embedding space formalism, which is necessary to construct these operators. Then in the next step, I will do precisely that, to construct these operators. In the second half of the talk, I'm going to present some examples of how we have used these weight shifting operators. For example, to raise the spin of an exchange particle in a correlator, or to raise the weight of the external particles, the external fields of a correlator. And finally, I will show you how to obtain inflationary bispectra with all these methods. So let's start with the introduction. What we want to do in this project is to compute cosmological correlators. We are trying to compute them at the end of inflation, and we are modeling inflation as happening in more or less the zeta spacetime. And we want to compute these correlators in this surface that corresponds to zero conformal time. We want to do this in order to use the correlators to infer information about inflation. And in particular, we are going to be interested in this kind of correlators that I have depicted here. This is a 4-point correlator, which corresponds to a process which is the spontaneous creation of a particle in the zeta, which then decays into other like particles like the inflaton or gravitons, which then leave their imprint in the observables. The way we want to compute these objects is purely from the boundary. We want to bootstrap them by using symmetries and by fixing their singularity structure. This is, for example, we are going to require physical singularities to be absent, and we are going to require the physical singularities to be there and to have the correct residues. And when it comes to symmetries, the symmetries that we are going to use are the symmetries of the zeta, of course. But the symmetries of the zeta isometries, it so happens that in the boundary they act like the symmetries of the conformal group. This is very nice because this means that the correlators that we want to compute, we can compute them by basically computing conformal correlators. And this can actually be done. We can compute correlators in this way, and this is very nice because we see that we are capturing the physics of the zeta, the physics of the bulk purely from the boundary. Okay, so let's start by seeing how one uses these conformal symmetries in order to constrain the correlators. So we are doing cosmology. This means that we have the translational, rotational invariances, and in order to leverage this, we are going to work in momentum space, of course. So if we think, for example, about the 4-point correlator scalars. These fields O are all scalars. We see that these invariances require us to write it as to write this correlator as proportional to a momentum conserving delta function times a function of the momenta, of the magnitudes of the momenta, and S and T, which are the magnitudes of these other intermediate momenta that we can have. For the case in which the fields are exchanging a scalar field, the dependence on T will not be there, so we can forget about it if we focus on this more simple example. Then we have to impose the invariance under the other conformal transformations, which are dilatations and special conformal transformations. And this gives rise to these two word identities, conformal word identities. The dilatation one is solved if we write this function f in this way. It's like the product of S, which is this momentum variable, to the power delta t minus 9, where delta t is the total conformal weight of all of these external fields, times a dimensionless function of u and v, where u and v are these variables that we define here. If we write the correlator in this way, the special conformal transformation word identity takes this form, which is a simplified form, as this differential equation in terms of these differential operators, delta u and delta v, that I have defined here. This is this is an equation that is possible to solve, and in this paper they actually solved it for the most simple case, which is the case of 4 external conformally coupled scalars exchanging a scalar field. So that is going to be the strategy. The strategy is going to be to solve it for that simple case that I have drawn here. As I said, these are conformally coupled scalars, so they have a conformal dimension equals 2. And then the way we are going to obtain the more complicated correlators, which involve spinning fields or fields with other masses, is not going to be by solving again the same equations for these other more complicated cases, but by using weight shifting operators. And we will apply these weight shifting operators on this more simple seed, and we will get the more complicated correlators in this way. So for example, by applying a differential operator that raises the internal spin, we will get this kind of diagram. Then by applying another operator that raises the weight of the external particles, the external fields, we will get a correlator in which the external fields have delta equals 3, which means that they correspond to massless fields in the bulk. And then, well, all of this we have done it in an exact de Sitter background. But of course, if we want to compute inflationary correlators, we need to change this. We need to break the de Sitter isometries at least weakly, and we will do that by taking this kind of limit of the 4-point correlator in order to obtain a 3-point inflationary correlator. This limit amounts to evaluating one of the legs of the correlator in the inflationary background. So in this talk, I will not describe how to compute this, how to solve the word identity that I showed before in order to get this correlator, but I will tell you how to construct these weight shifting operators. These weight shifting operators have been used in the conformal bootstrap in position space. This is a well-developed technology. What we have done here in this paper is that we have translated all of this technology to momentum space in order to use it for cosmology. So let's start by seeing how do people work with these weight shifting operators in position space. How do they actually construct them? And in order to do that, I first need to introduce the embedding space formalism. This formalism was first introduced by Dirac a long time ago already, but it was Weinberg who brought it back 10 years ago, and since then it has been used in the context of the conformal bootstrap. This formalism is also, by the way, well described in this review by Slava-Vitskov. So I recommend you to check it out if you want to know more about this. In this embedding space formalism, what we do is we are studying a Euclidean CFT in RD. We are going to embed this space in a higher dimensional space, which is Lorentzian. And this higher dimensional space will have coordinates capital X. And the embedding will be the following. The embedding, in order to do the embedding, we will restrict to the light cone in this higher dimensional space, and we will restrict to a section of this light cone, which corresponds to taking this light cone coordinate equal to 1. The coordinates that are left, we call them xi, and we will identify them with the coordinates of the lower dimensional space, so that the embedding has this form. And this is the magic of this embedding space. So now we can assign a light rate to each point in this section, and then if we do a Lorentz transformation in this higher dimensional space to points of the section, this Lorentz transformation we are going to define it by precisely a Lorentz transformation and then a rescaling back to the section. Then the points of the section after the transformation are related by a conformal transformation. In other words, these dx tilde and this dx are related to each other by a conformal transformation. So this means that we have transformed the action of the conformal group in this RD space, which is, well, pretty complicated. We have transformed it into the action of the Lorentz group in a higher dimensional space. This is the reason why this embedding space formalism is useful. So when it comes to fields, if we have a tensor field, for example, in the embedding space, and it satisfies these two conditions, that is homogeneous and the rescalings of the coordinates, and that it is transverse, this tensor field will project to tensor fields in the actual RD space where we have our CFT. And the projection is just this, where we are projecting on the section that I mentioned. We also use polarization vectors set, which are null and transverse, in order to contract with the Lorentz indices of these tensor fields. These fields and the rescalings will behave in this way. They will be homogeneous functions and the rescalings of the coordinates x with weight minus delta, and the rescalings of the coordinates z with weight s. Delta and s are precisely the conformal weight and the spin of the conformal operators that these fields correspond to. Once we have seen this, writing conformal correlators is really easy in this embedding space. The only thing one has to do is to write Lorentz invariant functions with the correct weights. So, for example, if we want to write the correlator of two scalar fields, 1 and 2, the only Lorentz invariant object that we can use in order to write such a function is x1 dot x2, because x1 squared and x2 squared are 0 because we are in the light cone. So knowing this, we see that we can only write things if the two conformal dimensions are the same. So the correlator will be 0 unless the two conformal dimensions are the same. And the only thing you can actually write that scales in a proper way is this function here. If the two operators have spin, then the thing is the same. You can write only two kind of objects with the correct scaling and the rescalings of the coordinate set. and these two objects are this and this, and the relative coefficient is fixed by transversality. And then the correlator is just this object here. In the same way, you can write 3-point correlators. They are totally fixed, and you can also try to write an ansatz for the 4-point correlators. And you'll find that they are defined up to an arbitrary function of 2 cross ratios. Okay, so we are now ready to try to build the weight shifting operators. These operators are basically differential operators, which will act on a representation of weight delta and spin s, and will give us a representation of weight delta plus alpha and spin s plus beta. These kind of operators, some of them were already found in this paper by Costa, Penedones, Polan, and Richkov. And then later they were more systematically studied in this paper by Karatev, Kravchuk, and Simons-Duffin. They found that generic conformally invariant weight shifting operators do not exist. So that if we want to find generic operators of this kind, we have to look for conformally invariant objects. So they studied the different representations of the conformal algebra. And for example, by looking at the vector representation, they found that these 4 different weight shifting operators can exist. One operator that lowers the weight by 1 unit and leaves the spin untouched. Another one that raises the weight and leaves the spin untouched. Another one that leaves the weight untouched and raises the spin. And another one that lowers the spin. And they are in the vector representation, so they have one free Lorentz index. And in the adjoint representation, in a similar way, you can find that these operators can exist. One that raises both the spin and the weight, another one that lowers them, and so on. You can also see that there are operators that do not change the weight or the spin, and they correspond to the conformal generators. So once you know that which kind of operators you can have, they are very easy to construct in the embedding space. Just because of the scaling properties of the fields in the embedding space, you know that, for example, in order to construct this operator that lowers the weight, you can write it as a sum of terms which have weight 1 and on the coordinates x. And in that case, and for the vector representation, the only kind of term that you can write is x with a Lorentz index m. You cannot write anything else. So this means that that the operator is just this. For the operator that raises the spin, for example, you can write 2 kind of terms. One is this and another one is this. And then you multiply them with some constants that you will later fix by using the property of transversality. In the same way, for the operator that lowers the spin, now you have 4 different terms, and so on. This is the way in which you can construct all of these operators, and all the constants can be fixed by transversality. Notice that we are not using, when we are writing these different terms, we are not using objects of this form, x dot ddx or z dot ddz, just because these kind of operators, they are just measuring the conformal weight and the spin of the operator they are acting upon, so they can be reabsorbed in these constants. Right, so once we have those operators in those representations, one can contract their free indices in order to create conformally invariant operators. Of course, one has to do this with operators that act on different points, different coordinates, x1 and x2, for example. And so the resulting objects will be conformally invariant operators which are bilocal. So for example, this one, this W++ is the result of contracting the operator that raises the weight at point 1 and with the one that traces the weight at point 2. So in the same way, one can construct the one that lowers the weight at the 2 points, and the same with the spin, raising the spin at the 2 points, lowering it at 2 points. And one can even combine different operators. So this operator, for example, raises the spin at point 1 and lowers the weight at point 2. One can construct more. And in the adjoint representation is the same story. One can construct, for example, this operator that lowers the weight and raises the spin at point 1 only. And this other operator that lowers the weight and raises the spin at the 2 points, at 1 and 2. One can construct more operators. I have listed these because these are the ones that we have been using in our project so far. Now, of course, we have done all of this in embedding space, but we want to translate it to Fourier space. But now this is really easy to do. We just have to go first to the usual position space by using the projection by projecting them on the section. And once we do this, it's straightforward to Fourier transform this, because we just have powers of the coordinates and derivatives of the coordinates. So in this way, we have managed to build a series of operators in Fourier space that will allow us to relate different correlators of different weights and spins. Okay, so now I'm gonna give you some examples of this. And I'm going to start by showing you how to start from a 4-point correlator in which the exchange particle is a scalar one, and obtain a 4-point correlator in which the exchange particle has a spin S. So what we have to look at here is at the two different vertices that we have. So, for example, in this case where the exchanged field has a spin, we have that at each vertex the process corresponds to one of these 3-point functions, where we have 2 conformally coupled scalars and 1 spinning field. This is for the case of spin 1, by the way. And using the weight shifting operators that I described, we can relate this to a 3-point function of just scalars. So, for example, here we have a 3-point function of the scalars, 2 conformally coupled scalars and another scalar that is related to the sigma. And then these weight shifting operators raises the spin of point 3, so of this O scalar, and lowers the weight of point 2. This means that the field at point 2 will no longer be a conformally coupled scalar, but it will be its shadow transform, because it goes down to conformal dimension 1. And then by multiplying with K2, we can get it back to a conformally coupled scalar, just because these and these are the shadow transform of each other. So this operator then is taking us from this 3-point function of 3 scalars to this other 3-point function in which the third field has spin 1. So this is the operator we are looking for, and this operator, as you can see, will be a differential operator on K3 and K2. But we can use momentum conservation on this 3-point vertex in order to rewrite all dependence on K3 in terms of K1 and K2. And in this way, we define an operator that we call S12 that acts on legs 1 and 2, just by using this momentum conservation. So this operator acts on legs 1 and 2, but it is raising the spin of leg 3. All right, so this was for spin 1, but it can be done for general spin just by applying this operator a number of times S that we need. Okay, so now that we know this, we can take the disconnected part of the 4-point function. So, for example, this is the 4-point function that corresponds to the scalars exchanging a spinning field. And this can be written in this way, with the 3-point functions that correspond to the two vertices contracted with the polarization tensor of the exchange field. Now, we know that these 3-point functions can be written like this in terms of the weight shifting operator acting on the scalar 3-point function. And if we take these operators and extract them, pull them out, this is possible to, this can be done. One has to be a bit careful, but you can pull these two operators out and notice that they are acting on the conformally coupled scalar only. One can group them with the polarization tensor in an operator called S, for example. And the object on which this operator is acting is just the disconnected part of the 4-point function of scalars exchanging a scalar, right? So we have derived this for the disconnected part, but this is actually valid for the whole correlator. So this implies that we can act with this differential operator on the seed, which corresponds to conformally coupled scalars exchanging a scalar, and we will get the conformally coupled, the correlation function for conformally coupled scalars exchanging a field of spin S. Now, this operator here can be decomposed in helicity components, actually. So we can, I'm not writing it explicitly, but we can write it as a sum on the different helicity components. So it will go from helicity 0 to the spin. And it is a sum of this product. This is a product between these functions pi, which we call polarization sums, and these functions encode the angular dependence of this function, and the differential operators that are acting on the seed. And these differential operators are actually not difficult to write. They are these objects here. Okay, so we have been able to compute these kind of objects, and now we want to go one step further and change the weight of the fields, of the external fields in this correlator. So we want to go from delta 2 to delta 3, which is the weight that corresponds to massless fields. And this is really easy to do. We just have to raise the weight of the 4 external scalars from 2 to 3. So we just use these W++ operators that I described before. And we use them upon the 4 external fields. If we write this, decompose in the helicity components that I said in the previous slide, we can then see how these operators act on each helicity component separately. And this is what I've written here. So these U12 and U34 are these W++ after commuting with the polarization tensors. With the polarization sums. So these U's are just these W's commuted through the polarization sums. I'm not writing the general expression for these objects, but it can be found analytically. It's just really long and messy. Okay, and once we have this is exactly the Sitter correlator, as I said. The only step left to do in order to get an inflationary correlator is to take one of the legs to be soft. But of course, these are massless fields. So this means that if we just take the soft limit, we will get an Adler zero. So in order to avoid this Adler zero, we have to slightly deform the mass of this external field. And we do that by deforming the conformal weight of the dual field. And we deform it by this small quantity epsilon. This epsilon is actually going to be the slow roll parameter. So in this way, we obtain an inflationary, a slow roll 3-point function. So this is the limiter we have to take. The only extra step that we have to do is sum over the permutations, because as you have seen, we are only studying the S channel here. But in order to obtain the inflationary bispectrum, we need to sum also over the t and the u. This is what this term means. So one nice thing here is that only the longitudinal mode of the inside of the exchange particle is going to contribute, because we're taking one of these legs to be soft, and this is a scalar. So just by angular momentum conservation, we have that only the longitudinal mode can contribute. Mathematically, this can be seen by looking at these polarization sums and taking the soft limit. You can see that that this limit is 0, except for the helicity 0 polarization sum. So this is very nice. This means that we can keep only the 0 term in this sum. So this is what we do here. And now we have to see what happens with this limit, in which we are deforming the conformal dimension of one of the fields. This limit affects only two elements of this formula. One is the seed. Remember that this seed is just the correlator of 4 conformally coupled scalars exchanging a scalar, and we are deforming the weight of one of the conformally coupled scalars. So this means that it won't be it will no longer be a conformally coupled scalar. And the other thing that is affected is this weight shifting operator, just because it depends on the conformal weight. But actually, if we look at the limit of this operator, we see that there is no need to perturb the seed if we are staying at linear order in epsilon. The reason is that when you take this limit on this weight shifting operator, the 0 order part of this expansion goes to 0 when one takes the soft limit. So this implies that this operator, when taking the two limits, just becomes minus epsilon. And so at linear order in epsilon, we can forget about perturbing the weight of the seed. The result is then this, just minus epsilon in place of this operator. And here we still need to take the soft limit on this part of the formula. But schematically, this is the result that one gets, and this can all be computed analytically and so on. This is the result for an inflationary bispectrum given by the exchange of a particle of any mass and any spin. Okay, so let me conclude now. We have bootstrap scalar cosmological correlators using symmetries and singularities, even though I haven't explained how in this talk. But what I have explained in more detail in this talk is that a series of weight shifting operators can be used in order to change the conformal weights and the spins of the fields in the correlators, and in particular used on this scalar cosmological correlator that we can bootstrap, we can get more general correlators. This technology has been imported to momentum space from the position space of conformal bootstrap, so it's a nice interplay between these two fields. And I haven't made it explicit, but by using this formula that I have derived, we can reproduce classic results, for example, by Maldacena, by Creminelli. One can also reproduce the trispectrum given by the exchange of a graviton and so on. But there is more. There are also new results that we have computed using this method and using these weight shifting operators. For example, we have computed the bispectra given by exchange of partially massless fields during inflation. And we have also computed the gamma zeta zeta and gamma gamma zeta, or contributions to these bispectra by using these weight shifting operators on the external fields, and for example getting the correlator of gravitons and scalars or gravitons and so on. We have done more stuff. We have also built correlators from lower point data in kind of a recursive way, using the consistent factorization of these correlators in some limits. And also using limits and knowledge about the singularity structure, we have constrained and ruled out theories. So if you want to know more about these three last points, I recommend you to see the talks by Austin Joyce. It will be a recorded talk, and the talk by Hayden Lee, which will be live during the second day of the workshop. So this was all. Thank you very much for listening. If you have any question, of course, you can ask me or my collaborators, and I hope to see you in the workshop. Thank you.